Welcome to another unit of the ISM course in Statistics 2. In this unit we're talking about regression analysis, and in particular if we have conducted a linear regression and we want to test whether our coefficients are actually significantly different from zero. Okay, why are we going to do something like this? Well, if we can show that the coefficient of any variable of any independent variable is significantly different from zero, this means that this variable has a significant impact on the dependent variable. That's why we're going to do this. How are we going to do this? Well, we're going to use like a small roundabout trick, and we're going to implement a t-test. So just as a reminder, with linear regression, we calculate coefficients or the intercept a and coefficients b1 till bk. We get the following regression line, which looks as follows. That's like for multiple linear regression. The question now is, are the coefficients different from zero? And is this difference from zero due to random fluctuations? Or is there actually a really significant difference from zero? So can we assume that the corresponding variable xi has a significant impact on the dependent variable? How are we going to do this? With t-tests. What are we going to test here? Well, we test whether one specific coefficient is zero or it's different from zero. So how are we going to conduct our t-test? Well, we need a test statistic. Well, if we recall with the t-test, in general, this just meant number of observations times, and then we had the arithmetic mean minus the testing value divided by the standard deviation. Here we're doing something similar. The only thing is the number of observations is already included, so we don't have to consider this here specifically. The average, so the arithmetic mean here, that's more or less our coefficient value, because that's only one possible coefficient. And that's actually the average of all coefficient or possible coefficient values we have. Okay, so that's our arithmetic mean. Our test value here is the value with which we compare the coefficient. That's here 0. So we only need the standard error. The standard error is like the pendant for the standard deviation. And then, well, we get a very easy test statistic, which is just coefficient bi here in absolute numbers, so without any sign, divided by its standard error. Okay, the standard error, this is a little bit more complicated. That's more or less the sum of all residuals divided by, then we have n minus 2, and then we have like something, well, let's say comparable to the variance. And if we do this, we get the square root out of this, we could get our specific standard error for each of our different variables xi and the corresponding coefficients bi. So we're calculating this test statistic, and usually you don't have to do all the big stuff with the standard errors. Usually the standard errors in one way or another, for example, if you use statistic programs, they are given already. Else you have to follow this relatively unwieldy formula for them. Okay, we have the test statistic, possibly with a lot of work, but the reference statistic is way easier. Here it's, as we know this, t, degrees of freedom, and then, well, we just have different from zero, could be smaller, could be larger, so it's two-sided test, so 1 minus 1/2 alpha. What about the degrees of freedom? So here we have the number of observations minus the number of independent variables, that's k, minus 1. And well, we find this value, as we know this, in the table for the t distribution. So again, the rows give the degrees of freedom, the columns give the 1 minus 1/2 alpha. So for example, here this value, that's for 1000 degrees of freedom and an alpha of 5%, of 0.05. Okay, so much for test and reference statistic. Well, if we have both, the test itself is relatively straightforward. We just compare both of them again. If the test statistic is smaller, we retain H0. If the test statistic is larger, as here is the case, we reject the H0 hypothesis. And that's all there is to this test. So let's take a look how this works out in an example. Here in the example, we have a study on the final results in an exam of 403 former students that used the final mark of the Abitur, X1, and the average time spent per week on side jobs, X2, resulted in the following regression line. And we have here the regression line. And we know additionally, for the standard errors, for the constant, a value of 0.04 has been calculated. And for the two coefficients of 0.2 and for the second 0.1. Our task, test for an acceptable margin of error of 5% if the two factors have a significant impact on the final result. Well, we do this because we have this for the constant as well. So what we're going to do is we get test statistics. Here we have 3 different coefficients, 3 different values, so we need to conduct 3 different tests. Calculate 3 test statistics. So for the constant, that's coefficient of the constant minus 0.1. We put this into absolute terms, so the minus is erased. Divide this by the corresponding error, which is 0.04, and we get a test statistic of 2.5. For the first coefficient, the B1, we have 0.6, that's the B1, divided by the standard error of 0.2, gives us a test statistic of 3. And finally, for B2, that's the coefficient of 0.01, divided by the standard error of 0.1, gives us here a test statistic of 0.1. So for each coefficient, we get 1 test statistic, but we only have 1 reference statistic. And that's here, Tn minus k minus 1, 1 minus 1/2 alpha. For alpha, we know it's 5% again. The n, the number of observations, was 403. We have 2 independent variables, so k is 2. So we have 403 minus 2 minus 1, so 400 degrees of freedom. And for the second term, we have 0.975. So if we turn to our table with the percentiles of the t-distribution, we go into row 400 and into the column 0.975. And there we find the value 1.9659. That's our reference statistic for all 3 cases. So we compare each of the 3 test statistics with this value. And that's our test decision making. So we see, if we combine this, in the first case, for the constant, the test value is larger. For the second case, for the B1, Abitur, the test statistic is also larger than the reference statistic. But for the B2, the side jobs, the test statistic is smaller. So this translates into the constant is significantly different from 0. B1 is significantly different from 0. But B2 is not significantly different from 0. So even though we have a value of 0.01, we cannot exclude that this difference results from random fluctuations alone. Okay, so summarizing this means only the final mark of the Abitur might have a significant or has a significant impact on the final result of the studies. For the side jobs, we cannot assume this to have any impact at all. And well, that's all there is to this example, all there is to this unit. So I hope you enjoyed listening to it. And if you're looking for additional units, additional exercises, feel free to visit the rest of the course or have a look at the corresponding playlist. I say goodbye and see you next time.